today I want to talk about my work, and I want to talk about computational social science. Computational social science sort of informs a lot of what we do with respect to agent-based modeling. And then I want to talk briefly about what is ABM, or agent-based modeling, and just give you some very simple examples so we're all on the same page, or slide, so to speak, with respect to agent-based modeling. But agent-based modeling is changing, and that's changing because of new sources of data. 10 years ago, or 15 years ago, the data that we have today just wasn't in existence. Social media, for example, or the extent of social media data. So I want to talk about how we're having new forms of data, and how this new data is basically giving us new lenses to study both physical relationships, how we interact in physical spaces, but also how we interact in cyberspaces and the connections between these areas. And this is also therefore allowing us to look at sort of linked spaces, the linkages between social networks and where you are physically. And then to sort of end the talk, I want to just give you some very quick overviews of some of the ways where we've been using open data for our own research, looking at humanitarian assistance, pedestrian movement, using CCTV data to basically calibrate a model, and then a model that we did in 2010, 2011 on border security, which might be of interest to some of the people in the room here. And what computational social science really is exploring social problems through computational methods. So the idea is we're using a variety of tools that are available to us: machine learning, remote sense imagery, network analysis, network science, if you want, cell automata models, agent-based models. We fuse these together to answer social science questions. And the idea is we're trying to build models. And why do we want to build models? We want to basically gain insights into certain types of social phenomena. The focus has shifted on looking at social systems from, say, the top-down aggregate types of models to sort of bottom-up models, where we're trying to capture individuals into these types of models. And one of the ways of doing that is agent-based modeling. I'll go into what is agent-based modeling in a little bit, but it's basically simulating a society or a group of people interacting with each other and seeing what happens over time, how these interactions go about. In agent-based modeling, these are computer simulations in general. So we're talking about creating an artificial world in our computer. We then populate this world with agents, people. These people are connected somehow through, say, social networks, through proximity or whatnot. And they all have basically rules. And these rules lead to certain actions occurring, and those actions lead to something emerging at an end. We're trying to build models to simulate people in these artificial worlds. And we can build models and explore a whole variety of different phenomena at a variety of different spatial and temporal scales. We can build models at a very fine scale, like pedestrian models, or my favorite model at the moment is a basketball model, using data from actually real basketball games. But these are like very fine scale models operating in seconds over very small spatial scales, like a basketball court or small areas. Or we can build models looking at, say, migration and things like that operate over a larger scale. Think about the Syrian crisis at the moment. That happen over years, potentially decades, and models anything in between these types of things. So these are the types of problems we can explore using agent-based modeling. By taking geographical data, we can go from a very simple model, say, this is a simple pedestrian model. So the red is people exiting a room. It's a very simple model. You can explore some very basic ideas, like if you increase the door width, how will that increase or increase the evacuation rate, things like that. But with real data, we can build more complicated models to account for, say, the actual built environment. So, for example, where are the staircases so this is first floor, second floor. There's a staircase from the first floor into the second floor, and the exit's actually on the second floor. So in this last example, we were asked we had a sponsor, EADS North America, now part of Airbus, to look at movement across the US-Mexico border, specifically part of Arizona. So I want to walk you through how we built the model and what goes on inside the model, a bit more of a deep dive. So we have Red and blue, the blue in this sense is customs and border protections and whatnot. The red here are smugglers of people or drugs or whatnot. The smugglers have their own paths. They carry in loads of people or drugs and whatnot, and they move them through the environment. You can sort of change the sensor network, the coverage. So the red is the coverage. You see lots of dots moving. That's like people on foot or doing patrols in cars and whatnot. We can see the smuggling corridors. And these smuggling corridors change depending on what's happening with respect to where the blue teams are operating. So if the blue teams are operating in one concentrated area, the red teams will move their operations elsewhere because their loads are being intercepted, and therefore they're losing money. But we can ask more about the model than just what's the impact of border security on the flow of people into the system. You can also ask questions like, which organizations are being impacted by being caught. So this is sort of the wealth distribution of different organizations as you go through time. You can work out, for example, loads potentially loads being intercepted, or people being intercepted, or potentially what's not being caught. Because even with all the efforts, people are still moving into this area. And we can work out what people are doing with respect to, are they on the way, are they fleeing, are they running, and things like that. So we can get a lot of information from these types of models.